Hi, folks. Today we're continuing with what we've done for the last couple of lessons, which is solving systems of linear equations. Today we're learning a third strategy. We're learning how to use elimination to solve equations. So we learned graphing first, then substitution, and today we're learning elimination. Elimination is the process of removing something. That's just a regular English definition of the word. This isn't a special math definition. The most common place where people come across the words elimination are maybe on the sports field, like we're going to eliminate our opponents, like from the sports bracket, um, or perhaps eliminating the enemy in a movie, removing them from the movie so they don't exist anymore. Um, Elimination is just the process of removing something. Before we start doing the examples of solving a system of linear equations, I wanted to do a couple more simple examples just to show you how this idea works, because the concept sometimes confuses students. So I wanted to start with simple examples, simple numbers that are obviously true. If I have an equation like 10 minus 4 equals 6, we know that that's a true equation. And another simple equation like 5 equals 2 plus 3. I can take these equations, I can add them together and still get an equation that's true. So I can take everything that's on the left side here and kind of add those together, where I would write 10 minus 4 plus 5. And that's still going to equal everything that I add to the right-hand side, which is 6 plus 2 plus 3. So to prove that those two are equal, I can kind of combine like terms. I can simplify each side of the equation. 10 minus 4 is 6, plus 5 is 11, and 6 plus 2 is 8, plus 3 is 11. I still have an equivalent equation. Basically, this works because I'm doing the same thing to both sides of the equation. When we subtract 2 from both sides of the equation and we divide both sides of the equation by 4, we're doing the same thing to both sides of the equation. That's all I'm doing here. Adding 5 to both sides of the equation is the same thing as adding 2 plus 3, because 2 plus 3 is 5. They mean the same thing. Similarly, just like you can add two equations together, you can subtract two equations. So using these same two examples, 10 minus 4 equals 6, and 5 equals 2 plus 3. I can choose to subtract those equations from each other. Okay, so I can subtract the equations from each other. So that would be 10 minus 4 minus 5 equals 6 minus 2 plus 3. Again, this doesn't immediately necessarily look equal, but they are. In fact, if we do 10 minus 4, gets us down to 6, minus another 5 is 1. 6 minus 2 plus 3, well, that's really 6 minus 5, and that equals 1. We are going to be adding and subtracting equations today, but sometimes it's not clear to students why this works, why we're doing it. So I wanted to start with examples where it was very clear what was going on before we started putting x's and y's into the equation. So let's look at how we can use this strategy of adding or subtracting equations to solve systems of linear equations. All right. We're actually going to do the same problem two different ways. We're going to use addition one time, and we're going to use subtraction one time. So for this, the first example, 3x plus 2y equals 4, 3x minus 2y equals negative 4. The strategy here is we don't want to just add or subtract any two equations. We want to choose our equations so that one of the variables disappears. Our goal is to eliminate one of the variables. And if you look right here, positive 2y and negative 2y, those two things cancel each other out. If I just add these equations together, then I'm going to get, let's see, 3x plus 3x is 6x. Positive 2y plus a negative 2y is the same as 2y minus 2y, which is 0. And then 4 plus a negative 4 is the same as 4 minus 4, which is 0. So in this case, coincidentally, I got rid of the 4 as well, not just the y variable. But the important thing is not to get rid of the 4. The 4 didn't matter. It was just a coincidence. The important thing here is I got rid of those y values. My equation now only has one variable in it. 6x equals 0. So I can solve for x by dividing both sides of the equation by 6, and I get that x equals 0. Now, remember, at this point, I had a success here, but the answer isn't, the equation isn't, the problem isn't solved because I know the x coordinate of my data point is going to be 0. Um, I know the x coordinate of my solution, but I don't have the y coordinate. How do we get the y coordinate? We take that x value of 0 and we go back and plug it back into one of the original equations. So I've got, I'll go ahead and use 3x plus 2y equals 4. I chose that one just because it had fewer negative signs in it, and maybe I don't like negative numbers, so I just choose the easier one. I'm going to plug 0 in where x is. 3 times 0 plus 2y equals 4. 3 times 0 is just 0, so I'm left with 2y equals 4. And to get y all by itself on one side of the equation, I divide by 2, and that gives me y equals 2. So now I know the y value is 2, so the answer is the ordered pair 0, 2. That point solves this system of equations. You can plug those values into both equations to check to make sure it works. But I'd actually like to show you how we can use these same two equations to eliminate a different problem, eliminate a different variable, and still solve this system of equations, getting the same answer. So this time what I'm going to do is instead of adding the two equations together, I'm going to subtract the two equations from each other. I'm going to, instead of adding that 3x, I'm going to subtract. Now the thing is, if I subtract one part of the equation, I need to subtract everything in the equation. What I need to do is basically multiply everything by -1. So, or kind of each term in the equation by -1. So here I'm going to be subtracting a negative, remember, which is the same as adding. And this term over here with the -4, I'm going to be subtracting -4. And remember, two negatives subtracting a negative is like adding a positive. So this time when I subtract the second equation from the first equation, 3x minus 3x, that's going to help the x's to disappear. So this time the x's are disappearing. I have 2y plus 2y is going to equal 4y. And I'm going to have 4 plus 4, which equals 8. The 0 just disappears in this case because we're adding 0. To get y all by itself, I divide both sides of the equation by 4, and I'll have y equals 2. This isn't the complete answer yet. This is just the y component of the ordered pair. I need to know what the x component is. How do I do that? By plugging this y value back into one of the original equations. So I will solve this by doing using this equation, 3x plus 2y equals 4. And I don't know x, that's what I need to solve for, but I'm going to replace the y with the value 2 that I got from the previous step. And what I get here is 3x plus 4 equals 4. Well, if I subtract 4 from both sides of the equation, 4 happens to cancel out on the left and the right side of the equation, and I end up with 3x equals 0. Divide both sides by 3, I get x equals 0, and that's the x value. So you can choose, for this particular equation, we did this example because it was easy to add or easy to subtract the equation. Normally, it's your job to figure out, does it make more sense to add the equations? Does it make more sense to subtract the equations? Also, sometimes there's an additional step you need to take before you can add or subtract the equations. So before we look at that next step, multiplying equations, let me just do one more example up here to show you how this works. So if I have a simple equation like 5 equals 2 plus 3, if I do something simple like multiplying both sides of the equation by 2, this equation is still an equation. It's still equal. It's still true. 2 times 5 is 10. And here, if I add up what's inside parentheses, that's 5, and multiply that by 2 is also 10. So multiplying both sides of the equation by a number still keeps the equation true. So what we're going to do is we are going to multiply one or both equations by a constant so that at least one pair of terms, the ones containing the x variables or the ones containing the y variables, are the same or opposite. They have the same or opposite coefficients. So 5 and negative 5, or 10 and 10, we want to have the same coefficients for at least one of the variables. So let's go back down to this example where we're supposed to solve this system of equations using elimination. And just looking at those very first terms, the x terms, negative 10x and negative 5x. If I just multiply both sides of this equation by 2, I will have negative 10x as my term that contains x in the second equation. And then that will be easy to add or subtract from the other equation. So let's do that. I'm keeping my first equation the same. Sorry, equals 1. And for the second equation, I'm going to use the distributive property here when I multiply the left side of the equation by 2. That's going to give me negative 10x minus 12y. And I also need to multiply the right side of the equation by 2. I need to do the same thing to both sides of the equation. So 23 times 2 is 46. Now, remember, the reason I did that was to get either matching or opposite coefficients on the x. These match, so I need to subtract my equations from each other. So I'm going to subtract negative 10, which is like adding 10. I'm going to subtract negative 12, which is like adding 12. And I'm going to subtract 46. There's no negative sign there, so it's just subtraction there. So negative 10x plus 10x is 0. Remember, that's why I chose these numbers, was so that the x would disappear. Positive 3y plus 12y is 15y. And 1 minus 46 is negative 45. I'm now going to get y all by itself. The 0 just kind of disappears here. And I'll divide both sides by 15 to get rid of the 15 and get y all by itself. And my y value is therefore negative 3. We now know that our y value is negative 3. But this isn't the final answer to what is the solution for this system of equations. We need to know the x value as well. How do we find the x value? by taking this y value and plugging it back into one of the original equations here. I'm going to choose the top equation. I'll use negative 10x plus 3y equals 1. And I'm going to plug that negative 3 in here where the y value is, keeping everything else in the equation the same. Negative 10x plus 3 times negative 3 equals 1. I want to solve for x, but first I want to simplify whatever I can. So I want to get rid of the parentheses here by multiplying. So I've got negative 10x plus negative 9 equals 1. Now I'm going to use reverse PEMDAS to get x all by itself. Adding 9 to both sides of the equation. We have 10 on the right side and negative 10x on the left side. So divide both sides by negative 10. And that gives you x equals negative 1. So my x value is negative 1. I now have an ordered pair, which should solve this system of equations, an x value and a y value. But just to make sure, I should check those values by plugging them into each of the original equations, not one of my modified equations, but an original equation. So let's check this first equation. Negative 10x plus 3y equals 1. My x value is negative 1. My y value is negative 3. So negative 10 times negative 1 plus 3 times negative 3 equals 1. And if we do the multiplication, we've got negative 10 times negative 1 is positive 10. Positive 3 times negative 3 is negative 9. And 1 is just the same as 1. That hasn't changed. 1 equals 1. That checks out. Let's test the second equation now. Negative 5x minus 6y equals 23. I know that my x value is negative 1, and I know that my y value is negative 3. So when I do negative 5 times negative 1, that equals positive 5. When I do negative 6 times negative 3, that's positive 18. And I should still have 23 on the right side of the equation. And 23 does equal 23. Oops, 23. So yes, that checks out. We now know for certain that this ordered pair is the solution to this system of equations. Let's do a real world example here of when we might use elimination. So we have a company that has bought delivery vans for two of its branches. We've got 5 large vans, 2 small vans for $235,000, and then a second delivery with 2 large vans, 3 small vans for $160,000. Again, just practicing which form of that linear equation makes the most sense in this example. Standard form works well when you have 2 items with different rates. This question is asking us for the cost of each type of van. So we have 2 different types of vans. Each van has a different cost, a different rate, a different price per van. So this is a good candidate for standard form when I have 2 different items with different rates, but I know the total. In this case, there's a total price depending on how many of each kind of van we buy. So I've got this kind of word problem laid out for us here of what numbers or what variables we're putting where. And let's focus on what the question is asking. We want to know the cost of each type of van. So if we've got large vans, let's call that X. So X is the price of large vans, and Y can be the price of small vans. So if we say X is the price of a large van and Y is the price of a small van, then all I need to do is multiply each of those numbers by the number of vans actually purchased. So 5 large vans were purchased, 2 small vans were purchased, and that was for a total of $235,000. That's what happened at branch A. branch B, we're going to have a separate second equation here. We bought 2 large vans, and we bought 3 small vans for a total of 160,000. I now have 2 linear equations, which we're supposed to use elimination to solve. And here, notice neither equation, like I can't multiply 2 times any particular number to get to particular whole number to get to 5. And I can't multiply 2 by any particular whole number to get to 3. So it's going to be hard to kind of match up these equations. It's actually perfectly correct to multiply by um, a fractional number. That still works for elimination. For the purposes of this, though, I am going to just modify both equations. I'll modify the first equation, I'll modify the second equation, and so we'll modify both of them until we get numbers that kind of cancel out. So for instance, if I want these y values to cancel out, I've got a 2 in the top equation, a 3 in the bottom of the equation. The least common multiple of 2 and 3 is 6. So what I want to do is I want to choose to multiply the top number by the value that gets me to 6y. So I want to multiply this top equation by 3. For the second equation, I also want to get the y to 6. How do I get the y to 6? By multiplying times 2. So I'm going to need to multiply the whole second equation times 2 to modify that equation correctly. So if I take this whole top equation and multiply times 3, I get, I get 15x plus, don't forget to multiply the next part by 3 as well, 6y equals, and 235,000 times 3 is 705,000. And now I'm going to do something similar with the second equation, but instead of multiplying by 3, I'm multiplying by 2. So 2x times 2 is 4x. 3y times 2 is 6y. And 160,000 times 2 is 320,000. I now have matching coefficients for the y variable, 6y and 6y. I want to subtract the second equation from the first equation so that the 6y disappears and I'm left with 0y. If I want to subtract this, I have to subtract all the parts of the equation. So I'm ready to combine these two equations using subtraction. 15x minus 4y is 11x. 6x minus 6y is 0y. And 305,000 minus 320,000 is 385,000. This 0y disappears, and we can just solve for 11x equals 385,000. So I'm going to divide both sides of the equation by 11. And I'll get that x equals 35,000. I now have an x value for the equation, for the ordered pair that solves the system of equations of 35,000. But my answer is not complete because I only know the x value. I need to know both the x and the y value for the ordered pair. So let's take this value of 35,000, plug it into one of the original equations, and see what answer we get. I like the second equation because the numbers are smaller. So I'm going to write 2x plus 3y equals 16,000. I'm going to plug that 35,000 in for x. So I've got 2 times 35,000 plus 3y equals 16,000. And now y is the only variable in this equation. So I can solve for y, but I should simplify what I can first. So I'm going to do 2 times 35,000 is 70,000 plus 3y equals 16,000. I'm sorry. I've been missing out on zeros here. That's 160,000. I miswrote it. 160,000. Now, to get y all by itself, I can subtract the 70,000 from both sides of the equation. And I get that 3y equals 90,000. And if I divide both sides of the equation by 3 to get y all by itself, I get that y equals 30,000. So 30,000 is the y value for this ordered pair that solves the system of equations. Once again, to be completely thorough, we should take that x value of 35,000 and the y value of 30,000 and plug it into each of the original equations to make sure they check out. They do, in fact, check out. I will leave that to you to check to see that that's true. But let's make sure we understand what this answer means in the context of this problem. Remember, we said that the X stood for the price of a large van. So this 35,000 is how many dollars? This is the price of a large van. Price of a large van. And this 30,000 we said was the price of a small van. So price of small van. So remember to be clear for yourself writing it on paper which variable means what so that you're not confused at the end about the meaning of your answer. I hope this